In this video, we're going to see how we can search for alternative optimal solutions in binary optimization, in optimization problems where binary variables are involved. We're going to try to find an alternative optimal solution for the Ohio Trust example that we solved, the location optimization problem. So it's always great if you can find an optimal alternative optimal solution. It's going to add to the options of the management, because sometimes there might be some other considerations other than the cost or profit. And if they can have two options that are equally good in terms of price or cost or profit, they can also consider other factors when they're making the final decision. So it's always great to be able to look for another optimal solution. So the way it works, and we're going to use the Ohio Trust location problem that we solved. Just to remind you, in Ohio Trust location problem, we were looking at a region with 20 counties, and Ohio Trust Company was looking at the minimum number of PPBs, principal place of business, in order to be able to cover the whole region, the whole county. We solved this problem. We found that they can do it with a minimum of 3 locations. Now, we're going to try and see if we can find an alternative optimal solution. When binary decision variables are involved, the process is as follows: the search process for alternative solution. We can find first we need to solve the original problem and find the optimal solution. Second step is to identify the variables that in optimality they took 1, and identify the ones that took 0. Right? So we basically divide the binary variables into 2 sets. And then third, we just add a constraint to the original problem and solve the new problem. The new constraint that we add is as follows: sum of decision variables in the set O, basically the ones that took 1 in the optimality, minus some of the ones that took 0 in the optimality, in the original solution. That has to be less than or equal to the number of variables in set 1. Here is just a number minus 1, whereas here was the sum of variables. So here is a list of decision variables. Here is just a number, a constant number, right? And the nice thing about this is that if you have a pure binary where all the decision variables in your model are binary variable, there's no continuous variable. If that is the case, this approach is guaranteed to give you either another alternative optimal solution or the second best answer. So this is important. So this is a powerful tool for when you are looking for an alternative solution in case of pure binary ILP, integer linear programming problems, where all the decision variables in your model are binary. So, which is actually the case with our problem, or the Ohio Trust Company problem that we solved in location optimization example, in location optimization application that we solved. So if you remember, this is the Ohio company, the list of 20 counties, and then we solved this for the minimum number of PPBs that are able to cover the whole region. We just solved this one, and we found that the minimum number that can cover the whole region is 3. All right. Now we want to add a constraint that helps us to find either another alternative solution, another optimal solution, but different, or to find the second best answer. what is the answer that is the second best. Is the second best basically. The is a little worse than this one, but still better than the other alternative solution. So I'm gonna add a constraint which will tell me this is the one. I'm gonna add this ones minus zeros should be less than or equal to a number of ones minus one. Number of ones minus one. So that's what we want to add is search alternative constraint. So it's going to be equal, the left-hand side is going to be sum of any variable that took one. So sum of this one, basically anything that you see that took one. All right, so I32, M32, and N32. So sum of ones minus zeros, sum of anything that you see zeros, comma, the 3, comma, and anything after this point. So that is my left-hand side, right? So I want this, I want to force this to be less than or equal to. Now, for my right-hand side, number of ones, I know that it's 3, right? I have 3 ones in the set of my binary variable. 3 minus 1. So I just need to type 2 here, 2. Just type 2 here. So here I have my left-hand side is a combination of all decision variables, all binary decision variables, because you can use this approach on mixed integer problems as well. All the binary decision variables less than or equal to the number of ones minus 1. So here you just put these, you just type the number. And now you just add these constraints to your, let me just call it alternative search constraint. All right, let me just go ahead, go to data tab, solver, and we already have our original solver, like the solver setup for the original problem. And I'm now gonna add the new constraint. Left-hand side less than or equal to the right-hand side, which is just the number 2. I can type 2 here. Okay, what this does, you can see here now in the optimal solution that this one is violated, right? It's not satisfied. So adding this will make sure to force one of these 3 ones, will force one of these to take 0. So that's the least thing that this will do. This will make sure that at least one of the 3 will become 0. So that's what we're doing by adding this. And like I said, it's guaranteed to give you either an optimal solution or a second best answer in case of a pure binary, which is the case here. All our decision variables in this example are binary. So I'm going to add this and I'm going to solve it. And again, we found a solution, but the solution is a little worse than our previous one. So you see here, it just forced, this one was 1. Actually, it doesn't have to force these guys to be to take 0, but it'll make sure that the at least if not possible for these ones to take 0, at least one of them, the ones to take 0, at least make sure to assign 1 to one of these zeros, which is actually the case here. The summit was 0 and now is 1. And that will make sure that this constraint, the alternative search constraint, is satisfied. So by having that, we now have 4 PPBs. We require 4 PPBs by having this constraint in order to be able to cover the whole region. So this will make sure that, I mean, from what I said, based on what I said, when you have pure binary constraint, it's guaranteed that what you find using this approach is the second best answer.